This lecture introduces epoxidation. An epoxide is a three-membered ring. Remember that it's a cyclic ether, and it's called either an epoxide or an oxirane. An epoxidation reaction is the formation of an epoxide, and it's usually formed through alkene oxidation. So the overall reaction looks like this, where you start with an alkene functional group, and you do an oxidation reaction to form the epoxide. Some common epoxidation reagents are peroxides and peracids. Each of these have oxygen-oxygen single bonds. Examples of peroxides are hydrogen peroxide and TBHP, which is tert-butyl hydroperoxide. And examples of peracids are MCPBA, and in MCPBA, the MC stands for meta-chloro, and that's the position of the chloro is meta to this group. PBA stands for peroxybenzoic acid, so this is derived from benzoic acid. It still contains the peroxide oxygen-oxygen bond. Another example is peracetic acid, and as the name implies, it is derived from acetic acid, and it's got a peroxide bond in it. Now pause this video and predict the products of these reactions before moving forward. In the first example, we've got an alkene functional group, and we've got hydrogen peroxide. Remember, this contains the oxygen-oxygen bond and can form an epoxide when it's treated with an alkene. So the product here is oxidation of the alkene to form the epoxide. In the second example, you're using peracetic acid, so this is an example of a peracid. Again, you've got this oxygen-oxygen single bond, which can do an oxidation. With an alkene, it can oxidize it to the epoxide. So again, the product would be an epoxide. So you've broken this alkene bond and you form two new bonds to the same oxygen. The mechanism of epoxidation is thought to be a concerted addition of the oxygen to the alkene. By concerted, we mean that all the bond breaking and bond making occurs simultaneously. We're going to start by analyzing our alkene. We know that an isolated alkene pi bond is nucleophilic, which means that we're now looking for the electrophile in this peracid. Whenever you see an oxygen-oxygen single bond, that bond is a very weak bond, and one of those oxygens is going to be electrophilic. This part of the molecule is the nucleophilic part, and it's going to pull electrons away from this oxygen, making this oxygen the electrophile. So the oxygen in red is the electrophile, and now we know that the nucleophile is going to attack the electrophile. Overall, we know that it's a concerted addition. The alkene is going to attack the oxygen, and so we've made this carbon-oxygen bond. As the alkene is attacking, we've broken this pi bond, and so now we've got a partial positive charge here. We need electrons to come in there, and those come from this oxygen-hydrogen bond here. And so now we've made the second carbon-oxygen bond. And when we made this first bond here, this oxygen-oxygen bond broke, and those electrons formed a carbon-oxygen double bond, which in turn broke this carbon-oxygen pi bond, and that grabbed this proton here. Overall, we've formed the epoxide, and in here we have made two carbon-oxygen bonds, and we've broken that pi bond, and we've turned the peracid into just the carboxylic acid. Due to this concerted addition mechanism, it implies that there is a syn addition of oxygen to the alkene. That means both of these carbon-oxygen bonds are formed from the same side of the alkene. The concerted addition implies that there is a syn addition of oxygen, and this implies that we have a stereospecific reaction, which means that the stereochemistry of the alkene determines the stereochemistry of the product. So if we start from a trans-alkene, we end up with a different product than if we started from a cis-alkene. Now let me redraw that trans-alkene to depict what I have in the 3D picture, and let's go ahead and predict the product if we epoxidize this. This is our carbon-carbon double bond. We have two methyl groups and they're on opposite sides. We can have a 50-50 chance of MCPBA attacking from the top or attacking from the bottom. Let's first draw what happens if it attacks from the top. In that case, we've made our epoxide on the top, and we've got the hydrogens on opposite sides. This hydrogen is coming out at us. The hydrogen is still going to be coming out at us here. And the methyl group is going to be going at the back. And likewise on the other carbon, we've got a methyl group coming out at us and a hydrogen going out at the back. Essentially, you can see that if the alkene is trans, then even the epoxide has those same groups on opposite sides. So looking at it again, we can see that if we have attack from the bottom, then we've formed the epoxide on the bottom. And if we put in the groups that are coming out at us, this is the hydrogen, this is the methyl, and then this hydrogen is going at the back, this methyl is going at the back as well. And so this is what happens when we've got attack from the bottom. If you look at the relationship between these two compounds, you can see that they are enantiomers. Again, if we start with a transalkene, so we've got the two methyl groups on opposite sides, we end up with an epoxide with the two methyls on opposite sides. Now let's do the same thing for the cisalkene, and I want you to pause the video and predict the product before moving forward. So the possibilities here again are attack from the top, and we have possible attack from the bottom. And we can draw the two products. So from the top, we've got the carbon-oxygen bonds are being formed from the top. Here you can see that the hydrogens are on the same side and they're coming out at us, which means in our epoxides, the hydrogens are on the same side and they're coming out at us. And the methyl groups are going at the back. Oh, that's going at the back there. So this is what we get if it attacks from the top. And then from the bottom, we've got our epoxide formed on the bottom, still hydrogens coming out at us on the same side, and still methyl groups going at the back on the same side. So you can see that if you start with two groups on the same side of the alkene, they're still on the same side of the epoxide. If you flip this over, you can see that this is the same compound, so these are both identical, and that's because it's a meso compound. It's got a plane of symmetry. This should be two equivalents of MCPBA here. Now go ahead, pause this video, and try to predict the products of both reactions. The first reaction contains sodium and ammonia, and these are reduction conditions for conversion of an alkyne to a transalkene. It does not affect other alkenes, and so the product is an untouched alkene here and a newly formed transalkene. We now treat this compound with two equivalents of MCPBA, so we can epoxidize both of these alkenes. This is a cisalkene, which means the groups are going to be on the same side, and this is a transalkene, which means these groups are going to be on opposite sides of the epoxide. So one possibility is if we have the epoxide coming out at us, and then for this transalkene, we can draw it so that we've got this hydrogen that's on the same side as this alkyl group coming out. This is your epoxide, and then the isopropyl group is going at the back, as is this hydrogen here. Now because we have two possibilities in each case, this can be from the top or the bottom, This can be from the top at the bottom. Overall, we have a mixture of 4 diastereomers. And so overall, we've got this compound, plus we've got the compound where this epoxide is going at the back. And then now we can do the alternative for the transalkene. So we've also got this combination and those are the 4 possible products.